Chapter 9 is where we'll learn about electrons and atoms. And it's going to be interesting. Electrons have a lot of really strange properties. Hopefully our goal in this chapter will be so that we can understand a little bit more about why certain elements have certain properties and so on, right? In chapter 4 and 5, we learned general rules of thumb that we just sort of told you that's the way it is. Like, you learned about how hydrogen is explosive. You produced some hydrogen in your gas lab and it's flammable. But noble gases like helium are pretty much completely unreactive. In chapter 4 and chapter 5, we learned how to figure out the charges for certain atoms, and we saw all the halogens form 1 minus ions. And we talked briefly about why that is in terms of transfer of electrons and valence electrons and stability and things like that, but we really wanted to get you going writing chemical equations and doing some of the more practical stuff first without getting bogged down too much in the explanations of the electrons. But it's going to be useful for us now to have this discussion about what electrons are and where they exist, the different areas in the atom that the electrons can be, and why the electrons have such an impact on the chemical properties of substances like that. So the problem, though, is that electrons are tiny, right? Even tinier than the protons and neutrons inside of the atom, right? Remember, the atom, most of its mass comes from the protons and neutrons in the nucleus, and those little electrons flying around outside of the nucleus have very little contribution to the total mass of an atom. So even atoms themselves are small, but electrons are way, way smaller. So we have no way of directly observing electrons, but we can figure out, or we can at least go through the story about how scientists over the last 100 years or so have figured out how electrons behave, and it all came about by studying light. And it makes for a good story in terms of how the scientific process was able to get us this kind of knowledge, but it's going to be useful for us to talk about light first, because it turns out that light and electrons share a lot of the same properties. In many ways, electrons are more similar to light than they are to the other particles that are inside of an atom, and so on. So let's talk about light. And when I just say the word light, of course you think about the light that comes from your lamp or from the sun or something like that, that is detected by your eyes, that allows you to see things, but it's actually a lot more than that. The best word to use is electromagnetic radiation, as any form of energy that travels in waves, and we'll talk about how that works, at a particular speed. And the light that our eyes can detect is just one form of electromagnetic radiation. So this number right here, 3.00 times 10 to the 8 meters per second, that's the speed of light. And it's a universal constant that all light travels at that speed. Now think about that. It goes 3 times 10 to the 8 meters in 1 second. So if we make an approximation here, if we shine a laser or some sort of light source out towards the moon, it would take 1 second for that light to reach the surface of the moon. And we can actually verify that because the astronauts on one of the Apollo missions left a set of mirrors on the moon, and they still do this experiment all the time where they can shine laser pulses at the moon. It goes over there, reflects, comes back to a detector about 2 seconds later. So on the surface of the Earth, though, light essentially travels instantaneously. It's way too fast for us to detect anything other than the instant traveling of light. Of course, I'm sure you know that that's why you see lightning before you hear thunder, right? It comes from the same event, but the light reaches your eyes very, very quickly, pretty much instantly to our sight, to our perception. But the sound takes a much longer time because that's just the motion of the air molecules expanding and compressing towards each other. The shock wave takes a much longer time to make it from the source to you. So let's talk more specifically about light. And here we're just talking about visible light. This is the difference between what red light is and blue light is. And it turns out if we could shrink ourselves down and actually see these waves of energy, they would not themselves look red or blue. I just sort of did that so that we knew what it is. The difference, though, is their wavelength. And wavelength, just the distance from either one peak to the next peak or one trough to the next trough, just pretty much the difference, the length of one of these wave cycles. Okay? That's about it. And we use this lambda. That's a Greek lowercase lambda. It's like the Greek version of L. So it's just like a length, but specifically when we're talking about the length of one of these waves, we use lambda and we call it wavelength. So the wavelength of visible light is on the order of hundreds of nanometers, and nano means 10 to the minus 9. So 750 nanometers, it's, if I do 750 times 10 to the minus 9, that's meters. That's the same as 7.50 times 10 to the minus 7 meters, if we just put that in the right kind of scientific notation. So it's almost approaching, right? Red light, if this were to go up to 8 to 900 and so, we'd get to 10 to the minus 6 meters. And to give you an idea of the size of this, human hair would be about 100 times wider than this. So 100 of these waves would be able to complete their cycles going from one side to the other side of tiny little human hair. So very small, but still quite a bit larger than atoms and molecules. These are on the order of 100 or 1,000 times larger than an atom or a molecule, right? Thinking about normal small molecules. So the wavelength is what determines what color the light is, but color is not something that is fundamental to that light itself. Like I said, red light itself isn't red. It turns out that our eyes are able to detect a certain range of electromagnetic radiation. The retina in your eye detects the different wavelengths, and our brain translates those different wavelengths into color. So color is just our brain's way of interpreting different wavelengths of visible light. So the color is just totally in our brain. The thing that is actually physical to the light, that is actually a part of the light itself, is just the wavelength of these waves. So you see, blue light has a much shorter wavelength than red light, and we can actually look at the visible spectrum to talk about everything in between. If I have some sort of regular incandescent light bulb, like with a filament in it, and we run that light through a prism will separate the different wavelengths of light, because when the light moves from the air to that prism, it travels a little bit differently, so that the colors of light with the shortest wavelength, like violet here, short wavelength, red light has the longest wavelength. Let's make that lambda a little better there. Look what happened. The violet light had its path diffracted the most. Eh? It turned the sharpest corner here because it has a shorter wavelength. Shorter wavelength light it's easier for it to sort of turn that corner. The red light with the longer wavelength made less of a turn through the prism, and everything in between gets sort of spread out like that. So there's an infinite number of colors. There's not just 7 of them. There's an infinite number of colors in the visible spectrum. That's what this is called. Ranging from red at the longest to violet at the shortest end of the wavelength, but with everything in between. So this is why you can see rainbows if the sun's light is reflecting through tiny water droplets up in the atmosphere. Those water droplets can act as a prism, spreading the different wavelengths of visible light out like that. So remember, though, that I told you that visible light is just only one part of the electromagnetic spectrum. Okay? This is all types of electromagnetic radiation, and here is the visible light, right in here. Just one tiny little band going all the way, though, from 10 to the 5th, these are meters, all the way down to 10 to the minus 15 meters. There's a minus there. Okay? So here is 1 meter, 10 meter, 100 meters, right? 1,000 meters, right? Over here, you're getting around the distance across the country. Here is almost the distance across the planet, right? So, ranging all the way down to a fraction of the width of an atom. Okay, so if we look, it goes from longest wavelength, again, here with radio waves of the longest wavelength, to shortest wavelength on this side with gamma rays. But now this chart also shows us the relative energies of those different types. So the side here with the radio waves, those are the lowest energy forms of electromagnetic radiation, where gamma radiation, gamma rays, are up at the high end. So this relationship between energy and wavelength is an inversely proportional relationship. And that means whenever something is inversely proportional, that means as one thing increases, the other thing decreases. So as we go from lowest energy to highest energy, the wavelength actually decreases. The wavelength gets shorter. Okay? Or as you're going to longer wavelengths, it has lower energy. And one way to think about that, because all of these are traveling at the same speed, these are all traveling at the speed of light, if you have very long waves, it will take a while before one wave makes it through a point and the next wave makes it through, and so on. Okay? If you've got these coming into contact with something, your hand or a collector or something like that, one wave will take much more time to pass through, as opposed over on this end, where the waves are very short. Since they're still traveling at the same speed, there will be many, many, many waves that pass through a point in any given period of time. So you can think of over here, many more waves are hitting in any point in time. That's why they have higher energy. And another way of saying that is that this side is high frequency. This side is low frequency. Frequency is just how many waves pass per second or something like that. So frequency and energy are directly proportional, okay? But both of these are inversely proportional to wavelength. Wavelength is the opposite to all those other ones, okay? So let's just briefly talk about the different forms of electromagnetic radiation, starting over here with radio waves, which again have the longest wavelength and the lowest energy. And of course, radio waves are what transmit all of our electronic communications. So the radio and TV signals, your cell phone signals, all those are being transmitted as radio waves, which are able to be sent very efficiently for hundreds of miles or so from a transmitter in some cases. So microwaves, though, are only one step above radio waves. Okay? So they're the second lowest in energy of all these things. So I imagine there are many of you whose mother has told you not to stand too close to the microwave. Your mother's just trying to protect you, so that's not a terrible thing, but in this case it's maybe a little misguided, because microwaves really aren't going to hurt you standing next to the microwave, because microwaves themselves are so low in energy compared to even visible light. Microwaves have less energy than normal visible light coming from a lamp. Well, then you ask, how is it they're able to cook my lean cuisine? Well, microwaves are special in that they have the exact right wavelength in order to get water molecules moving. Okay? Let's just say the energy is just right. to make water molecules move. And the way that works, imagine you're pushing a kid on a swing. You have to get into rhythm with them as you're pushing, right? You have to be pushing just at the right time in order for them to start going higher, and so on. If you're just pushing at random times, you're not going to be helpful at all. So with microwaves, it turns out that water molecules have a certain rate that they like to move at, right? They sort of vibrate back and forth, and microwaves are coming at those water molecules at just the right times so that the water molecules can start moving. It also works a little bit with fat molecules and some other things, but if you just put a piece of paper or a piece of cardboard in a microwave, nothing would happen. There's nothing in there that those microwaves could start moving. So the door on a microwave, it's not just glass, right? Look at it again closely the next time you use your microwave. It has a bunch of little holes in it. It's a metal screen with holes cut in it. If we look at the wavelength of microwaves, okay, right about in here, these are meters, right? So that's 10 centimeter, that's 1 centimeter, that's a millimeter, okay? The microwaves in your microwave oven are about 5 centimeters in length or so. So those microwaves are far too large to fit through those little holes in the doorway. So you're perfectly safe watching your food cook in the microwave because they can't get out through those little holes. Visible light, which has a much smaller wavelength, has no trouble making it through those holes, but the microwaves get stopped by them. So if you were to somehow stick your hand in the microwave while it was on, it certainly wouldn't be pleasant because the microwave would start to get the water molecules moving in your hand and you could get burned from it. But honestly, it would be no different from sticking your hand in a pot of boiling water. You're not going to get cancer from doing that. You won't grow an extra finger or anything like that. It's just a method of heating up water very efficiently. So let's keep going here to infrared. Infrared behaves just like visible light for the most part. Let's say behaves like visible, except you can't see it. Our eyes are tuned to accept only a certain range of light wavelengths, and infrared is just slightly too long for our eyes to be able to see it. But otherwise it works a lot like visible light does. If you have a remote control for your TV, there's a little light on the end of it that blinks infrared light. That could just as easily be a little red light on the end blinking that your TV would detect, but it's just much less annoying if it's blinking something that your eyes can't see. So it's shooting out infrared light towards your TV that tells it to turn on or change a channel or something like that. So then we got visible light. We're familiar with that. Ultraviolet, X-ray, and gamma rays are the ones that have shorter wavelengths than visible light. And what I'm going to say about these is that once we get into ultraviolet, X-ray, and gamma, these are the ones that themselves become harmful. Okay? Of course, anything in a huge amount could be harmful, right? A large amount of visible light could be harmful. If you put your hand in front of a huge spotlight, eventually it would get heated up enough where you could get a burn or something like that. But even moderate amounts of these ones can be harmful in certain circumstances. So ultraviolet light, it's given off by the sun, and anytime you get a sunburn or even a suntan, in fact, that's your skin's response to being damaged by the ultraviolet radiation given off by the sun. So once we get into this harmful range, the light has enough energy in it to start damaging molecules in your skin or in your body or something like that. It turns out ultraviolet light can start getting the DNA in your skin cells to start replicating incorrectly. So that's where skin cancer can come from. But even if it's a small amount of damage that it causes to your skin can produce more pigment as a result That's how you get a suntan, because then that pigment would be absorbing some more of the ultraviolet as opposed to it going in and damaging your skin. But still, that's your skin's response to being damaged by ultraviolet light. There's no healthy way about getting a suntan from the sun, or from, even worse, from a tanning booth. So in fact, in our lab, the sanitizing cabinet where you put your goggles has an ultraviolet light in it that's able to kill all the bacteria and the fungi and other nasty things on glasses. So X-rays are interesting because they have just enough energy to go through soft tissue, but they're stopped by bone. So if you've got an X-ray source on one side of your hand and an X-ray detector on the other side of your hand, it's going to be able to see where it goes through the soft tissue, but it's going to be stopped by the bone. So you get a nice picture of your bones, and you can see where your bones are broken or something like that. So yes, X-rays themselves are harmful, but a normal X-ray of your hand or even your chest or something like that is so quick, it's such a small amount of X-rays that you'd probably have to get hundreds of them before there was any measurable increase in your danger for cancer or anything like that. Now, CT scans are different. You know, they take a whole series, hundreds of X-rays through slices of your head, essentially. So your doctor or radiologist is always going to be concerned about how many CT scans you're getting in a year or something like that. But people that administer X-rays will always wear protection because they are doing that many, many times a day, and over the course of a career, if they weren't protected, they would be at an increased risk for cancer or something like that due to damage from those X-rays. But a couple of X-rays on your hand or something, you don't have anything to worry about. Now, gamma radiation, it's given off anytime something undergoes radioactive decay. So let's just say nuclear weapon. That's the worst case scenario for gamma radiation. The incident at Fukushima, the power plant in Japan, where they had a meltdown of one of their nuclear reactors, the very brave people that went into there right immediately after to get the water flowing again to cool it down were actually subjecting themselves to pretty harmful levels of gamma radiation. Now, everybody in the several mile radius around that nuclear plant is not subjected to gamma radiation. That only comes from a direct nuclear material, like a weapon or nuclear fuel cores or something like that. Everybody else, in the 10 miles or 15 miles or so around that may have been subjected to nuclear fallout, which is radioactive isotopes of iodine and cobalt and polonium and other elements that are radioactive. But those just sort of rain down as dust and fall down onto the surface of things. So those can be harmful if you ingest it or if you breathe it in. Okay? But if you've got a face mask on and if you get scrubbed down or something, there's no real danger from that. There is danger from crops that are grown in that area, so that's why they're having to scoop out the first couple of inches of soil in that whole area because that has contaminated radioisotopes in it. But again, that's not gamma radiation. Gamma radiation comes from a direct nuclear event, like a weapon or fuel rods or something like that, directly. And gamma radiation, of course, can be very dangerous. So what I would like you to know is the order of these. Okay, so know what order they go in, but also know the trend of wavelength and energy. Okay, I'm going to add down here at the bottom, of course, that gamma radiation has the shortest wavelength and the highest energy. Right? So I could ask you what has higher energy, radio waves or microwaves, or I could ask what has a longer wavelength, infrared light or visible light. Okay, here in the infrared spectrum, right, we could do the exact same thing. I could ask what has a longer wavelength, red light or green light? What has higher energy, green light or blue light or something like that? So it follows the same trend. This is just an expansion of that little area in here. So these are the longer wavelength ones, okay? But these are also the lower energy ones over here on this side. And we'll talk more about that as we continue on. That'll come up again for us.